Okay, time to get started. So we're actually going to do a little bit of Math 212 material now. We got all the preliminaries out of the way. So we'll start off a very quick comment. This is the first thing to say in the chapter about vectors. I believe this is the title of the chapter. But first we want to tell you what points in Rn are. I mean, what is Rn? Y'all have probably done a lot of things in what we call R2. Y'all probably call it the XY plane. Right? The choice of X and Y as those variables is super arbitrary, super unimportant, right? So we prefer to call it R2 because we don't want to impose such a choice on the user. R2 refers to, well, the collection of all ordered pairs of real numbers. Right? Okay, so now, of course, those ordered pairs, if you want to view them geometrically, right, you can take x1 as being this, coordinate along this axis. You can take x2 as being this coordinate along that axis. And then this ordered pair, this combination, you can interpret then as the point. Right? So that's hopefully a very familiar concept. So you can do the same kind of thing, though, with more than two real numbers. So you can talk about R3. R3 is just a collection of all ordered triples, for which there are therefore three axes, defining coordinates then of a point in space, right? Which you might want to call a three-dimensional space. Excuse me. Okay, so not that big of a stretch. That's going to be geometrically different, sort of a little bit more geometrically demanding to think geometrically in R3 as opposed to R2. But it's really just kind of the same idea, just a little bit more so. Okay. By the way, so again, the variables that you choose, whatever, it kind of doesn't matter. I mean, anyone who's taken an econ class knows that economists very often, instead of using X and Y, will use like P and Q or something, and depending on your situation, you might not be interested in how Y and X relate. You might be interested in how L and alpha relate, something like that, right? So let's not get bogged down in what the variables are. I like to, if there's no particular reason to choose anything else, why not use X1 and X2? It seems very natural to use indices to distinguish the variables, but whatever. All right. Okay, moving along.
Can't see those trees.
Oh, what happened there? Okay, that's weird. You know what happened? I probably touched the little thing there with my elbow or something. Sorry about that. Okay, yeah. If that happens again, please let me know. Thank you. Yeah. Okay, so what about not just R2, not just R3? What about R4 or R5 or R27? Right? What's that? Well, good news, in the same way that R2 is just an ordered listing of two variables and R3 is just an ordered listing of three variables, well, it's not at all hard to extend that algebraically and say that Rn is just all ordered lists of n real numbers. What's the problem? There's really no problem algebraically. Right, now the problem comes up when you want to visualize this geometrically. What does this look like? Where's the picture that I would point to? And I couldn't begin to possibly hope to be able to visualize Rn if n is anything bigger than 3. Right? Okay, maybe 4. You might be able to make the case that if you look at things a certain way, and if you've got some sort of gift of geometric visualization, and if you make arguments by analogy, then you can kind of, maybe visualize 4 dimensions. A little bit, maybe, right? Forget it beyond that. Right? Okay. All right. So, but don't be oversold on this disappointment. The fact that we can't visualize it geometrically doesn't mean we can't talk about it algebraically. Furthermore, the fact that we can't visualize it geometrically does not in any way suggest that it isn't useful in our world. Right? A lot of people make the mistake of thinking you don't need to know the math beyond 3 dimensions because, for crying out loud, we live in 3 dimensions. How could we possibly ever need to know about, R7? And there's easy examples, right? If you take an econ class, they'll write down economic models, algebra, relating variables, of which there are more than 3. Right? I mean, they'll relate interest rate and risk and profit and revenue and tax, whatever. I don't know any econ, right? But I mean, you could enumerate all sorts of economic variables that all relate to each other. Well, you're doing math in R9 all of a sudden, right? So, yeah, it's too bad that we can't visualize it geometrically. But being able to define it algebraically, being able to do math, get stuff done in RN, extremely relevant, extremely applicable. This is not just a bunch of ivory tower mathematicians, speculating about the irrelevant. It's extremely natural. Okay. Good news for you guys, we're not going to do much in RN. We're going to pretty much focus on R3 and R2. But I think it's very important to realize that, most, not all, sadly, but most of what we do in this course in R2 and R3, there is an analogous version of that in higher dimensions. And they're usually pretty darn analogous. Okay. All right. So that's points. Now we're going to actually go and talk about vectors. So first, a definition. Vector is a direction and a magnitude. Has anybody seen the Despicable Me movies? Mm-hmm. Yeah, there's a character. Yeah, right. There's the whole. I'd play the video, but then I'd be afraid that I might get taken down off of YouTube, right, for copyright violation or something. I don't know. So anyway, they stole that idea from us, and not vice versa. So here's some examples. Why would we care about this particular little mixture? A direction paired with a magnitude, what has that got to do with anything? Well, here's some pretty natural physical notions. Displacement. Right? This is a very familiar concept. The idea that you would want to, from wherever you might happen to be, change your position in a certain prescribed way. Such as, I could, wherever you might happen to be, you could say, walk west by 20 meters. That's a direction, west, and a magnitude, 20 meters. Okay? So a vector, whatever that is, this particular combination is the perfect mathematical tool for representing the physics concept of displacement. Okay, ditto various other things. Velocities. If you have a velocity, you're moving in a certain direction. The magnitude is the speed instead of a distance, but that's still a magnitude. It's an amount of, how much is it that you're moving in a certain direction. Forces, direction and a magnitude. Gravity is applying a force to my laptop stylus here. And there's a direction, gravity is pulling it down, and there's a magnitude, namely how much does this little thing weigh. Okay. Flows of fluids. You can define this in different ways, but if you have a fluid flowing, so for example, let's take the air in this room, right? At any given point, let's say this point right here, the air is flowing in a certain direction, and you could try to talk about in some way, what's the magnitude of the fluid flow in that direction? At this point, is the air going? Is it going really fast, or is it just kind of a gentle movement? How does that? How much flow is there? You can quantify that in different ways, but there will be some sort of a magnitude that describes that. And one way to do that is to talk about per unit area. Like if I were to put a little area here, how much fluid per unit time is passing through that area? That'd be a reasonable way to do it. Another very reasonable way to do it would be to just talk about what's the speed of the fluid itself, any little particular piece of the fluid, how fast is it moving? Different ways to go. Okay. So now let me skip ahead real quick. Here are some pictures. There's a temptation to look at this and see 3 vectors, because look at that. That has a direction and a magnitude. So you're going to want to say that that's a vector, and then you're going to want to say, well, this distinct thing here is also a vector because it has a direction and a magnitude, etc. You feel like you see 3 vectors. In fact, this is all representing the same vector. There is only one vector in this picture. There are 3 different arrows, right? But those 3 arrows are all representing the same vector because they are pointing in the same direction. They are all of the same magnitude, or at least that was my intention when I was drawing this. So work with me. Let's to the limit of my artistic ability, they all have the same magnitude. So same vector. So that's 3 different representations of one vector. Everybody on board? So don't make the mistake of conflating vectors and arrows. Arrows are a wonderful tool for representing vectors because arrows do have directions and they do have magnitudes by virtue of their length. How long did we draw them? But they also awkwardly have another characteristic. Arrows have locations. Right? That's not on the list. Vectors are not directions, magnitudes, and locations. Vectors are just direction and magnitude. Right? So vectors and arrows are related, but they're not the same thing. So do keep in mind, this is one vector. Okay, all right. Now, so we've talked about points. We've talked about vectors. They're very different concepts. Right? I mean, there's pretty clear. Points are locations. Points don't have directions. Points don't have magnitudes. That's not what a point is, right? Vectors have direction and magnitude, but they don't really have locations, per our discussion a second ago. So these are different things. Let's not lose sight of that. In other contexts, they're not only not the same thing, but they're not even particularly closely relatable. They're very different things. However, here's the thing. In Math 212, we're going to be doing all of Math 212 in RN, usually R2 and R3. So in this limited context, even though they are different things, there is a natural correspondence. There's a one-to-one, pairing. You give me a vector, there is a corresponding point. You give me a point, there is a corresponding vector. Again, they're different, but they line up perfectly. So let me show you how that works. If you give me a point, well, here's the thing. That point, there is, in fact, a unique arrow whose tail is at the origin and whose head is that point. You give me a point, then there is this uniquely defined arrow. Critically, by the way, tail at the origin. So if you give me a point, there is a well-defined arrow. And of course, an arrow, it has a location that we're not interested in, but that arrow has a direction, it has a magnitude, and therefore it defines a vector. So I'm going to, kind of highlight all of those because they all represent the same vector. You give me a point. By using the origin as a tail, we can define then a vector. Everybody on board? By the way, this is vice versa. If you give me a vector, right, here's a vector, direction and magnitude. It's represented by lots and lots of different arrows. Exactly one of those many arrows representing that vector will have its tail at the origin. That unique arrow with its tail at the origin will have its head at a certain location that is the corresponding point. Okay, so roughly speaking, the natural correspondence between points and vectors is the arrow with its tail at the origin. Okay. All right. So here's some notations to represent vectors. If you have, let's go back to green here. This vector here. You could give it a name and call it V. It's very common to put a little arrow hat on top of it. That's just kind of a visual reminder to the user, to the reader, that hey, don't forget this V. It's not a number. That's not 6. That's a completely different object. Namely, it's a vector. So that little arrow is very common in introductory math classes. I will point out that in different fields, they just don't do that. They think that's weird. And in more advanced math classes, this gets viewed as kind of a training wheels kind of thing, and nobody does it beyond a certain level, right? That said, I think it's really convenient and really useful, and some of the kinds of constructions that kind of the algebraic constructions that we're going to be dealing with, it is very handy to have a clear visual cue of what in your algebra is a vector, what in your algebra is a real number, what in your algebra might be a different kind of thing altogether, right? So I'm going to suggest we do that. Another alternative little visual cue indicating that something's a vector is to write it in bold. Our textbook does that a lot, which I think is rude. because they can do it with typesetting, but we can't do it with a pencil very well, right? And I just don't think it makes any sense to every time I want to refer to the vector v, I've got to, get real thick with it takes several seconds then to write your vector. So the book is establishing a precedent that's extremely inconvenient for us to emulate. Rude. So I don't do that, but heads up, the book is going to do it that way, and so you need to be familiar with it. And all of everything that I write and all the stuff that I am going to typeset, I'm going to use this notation here. Okay. Now don't forget, vectors correspond to points, and points, as we discussed earlier, have coordinates and can be represented with ordered lists, pair in this case, because these are two-dimensional vectors, so two-dimensional point, two coordinates. Well, here's the thing. If I write this, x1, x2, that clearly represents a point, and then by way of this correspondence, it could be viewed as also indicating that vector. Right? Certainly there's only one vector that's associated to that point, that's associated to that notation. Right? So that's another reasonable way to write it. Now, some people don't like the sloppiness of conflating these two different things. After all, points and vectors are not the same thing, right? I mean, we agreed to that. So they're not the same thing, but nevertheless, indicating the coordinates of that corresponding point, ultra handy. But so the solution there is to use a different kind of, very similar, but just aesthetically different notation of triangular braces instead of parentheses. And so triangular braces x1, x2 indicates the vector that corresponds to the point with coordinates x1 and x2. Feel free to do that if you'd like. I don't. I'm never confused as to which one is being referred to by virtue of the fact that they have entirely complementary characteristics. Points have locations. Vectors have directions and magnitude. They don't have a location. Right? Points don't have direction or magnitude. So, whatever it is that you're referring to, whatever role, the thing that you're describing with x1, x2, how it's being used should make it perfectly clear in context. Are you talking about a vector, or are you talking about a point? And so, since the context always makes it clear, I'm pretty comfortable with just being sloppy with the notation. I'll confess it's a little sloppy, but anyway, so don't worry about it. For reasons that'll become clear eventually, for very small reasons very soon, and for bigger reasons much later, sometimes instead of writing your ordered pair horizontally, sometimes it's useful to write it vertically. So be aware of that. I actually do that a lot, and it's convenient in a lot of ways. So, okay, alrighty, how are we doing? Everybody on board? Feel free to raise your hand, ask questions as we go along. I have a tendency to, fill up all of the time. It's hard to butt in when I'm talking. I ask my wife. So feel free to raise your hand. I'll be happy to entertain a question. Okay. Here's another little bit of sort of algebraic sort of feature of vectors. Let's talk about how to compute the magnitude. Well, there's a convention that we use. If you want to represent a vector, well, again, we've agreed that we represent vectors with arrows because direction and magnitude, right? Arrows have a length. And so the convention is, in some contexts we don't follow this rule, but for the purpose of what we're doing here, the convention is that whatever is the magnitude of the vector that you're describing, represent that geometrically by it being the length of the arrow that you use. All right. So that said, if I want to know, what is the magnitude of the vector? Well, the magnitude of the vector is the length of that arrow, but that's the hypotenuse of this triangle. And I know how to compute the hypotenuse of a triangle. All right, so there's your formula for the magnitude of a vector. Here's the three-dimensional version of that. Now, why is this true? Is this true simply because it's algebraically kind of analogous to that? Absolutely not. Algebraic analogy is not a proof, right? Very often, algebraic analogy is completely false, right? So be careful with that. So why is it that this is true? Well, this is something that's kind of a little geometry problem, and I'm going to leave it to y'all to do that geometry. I'm going to give you a hint on how you would go about in this three space here. How would you go about computing that distance? And the idea is to recognize that even though this is not a triangle, right? But there are, I can say instead, a pair of triangles that you can entertain. And if you write down the Pythagorean formula twice and carry it through carefully, solve for yellow, you will get this formula. I guess I have to zoom out. So this is a really nice exercise. By the way, this is also a good segue. Very often in this class, I will leave something for you guys to work out on your own. And I strongly encourage that you actually do those. I'm not going to hit it real hard every time like I'm doing right now. But the reason I want to make sure that you do this kind of thing on your own is because this is nice practice. This is nice practice. Are you visualizing these things the right way? Are you seeing the connections that I'm trying to point out and that I want you to see? Actually cranking it out, writing it down, pen to paper, is a good sanity check that you're getting what I want you to get. Also, here's another sort of coincidental thing. I tend to leave things as exercises to students that I think are both interesting and that you can reasonably be expected to be able to accomplish. And here's the thing, when I write exam questions, I tend to go for things that are interesting and that I think you can reasonably be expected to accomplish, right? So they tend to, I don't want to say they're always the same thing. I'm not saying that I will always include, every test will include at least one question that was a suggested, exercise for the students. But it's happened before just by coincidence. Because this is just, again, it's the same thought process, right? So just if only strategically, I think it's a great idea to actually do those kinds of things. So give this a shot. Be good, definitely be worth your time. Okay, so let's talk about addition. What should it mean to add two vectors? Let me emphasize my use of the word should here. Would not be reasonable to say what happens when you add two vectors. It's not reasonable to say that yet because we don't have such a definition. Now, y'all are accustomed to the idea of addition, right? But let me point out that you can only add things for which addition has been defined. So y'all know what it means to talk about 3 plus 7. Right? That's a thing that's long since discussed a long time ago. You know what plus means. You've memorized your addition tables, etc. But what is bicycle plus frog? It's garbage, right? That doesn't make any sense. That's not a thing. There is no such addition, right? Okay, so notice what we have here. This is two new things, right? A vector, we just defined it, right? You can't say, oh yeah, do that whole elementary school thing to these two vectors because those aren't things that were ever discussed in elementary school. The addition that y'all have used your whole lives, as of the moment, doesn't know anything about what it would mean to add those things any more than we could add bicycle and frog. It hadn't been defined. It's not a thing. So it's not a question of what happens when you add them, like adding them is something you can do and we're just trying to predict the result. We are at a point where there is no pre-existing meaning for addition of vectors, and we're going to choose. We get to decide. Right? This is a brand new idea. Okay. All right, so how are we going to make that choice? I have a silly story I like to bring up at this point. When I was a kid, I think I was 6 or something, I don't know, first grade-ish. Whenever you're learning multiplication tables, is that first grade? Anyway, whatever. Very young. forgivably young. I was learning my multiplication tables, and I was very frustrated by the fact that 4 times 7 was 28, right? Because it's like, why? Who came up with that? What's the point there? And I had this, what I at the time thought was a brilliant idea. How about phooey on that? Let's just make it 47, and boom, multiplication is so easy. It streamlined the problem, right? I was very proud of myself. Everybody see the motivation there? And I know you see why that's ridiculous, right? Again, I say forgivably young. I was like 6. What do you expect? So why is 4 times 7 28? Well, it's an arbitrary definition, but the very first time someone defined multiply, it was a brand new thing. They got to decide whatever they want. Why did they choose this? Answer. Because if that's 4 and that's 7, then this area is 28, and you can just, subdivide and just count up the little squares, right? And there's 28 of them. So, said differently, multiplication, this concept, this algebraic construction of multiplication was chosen based on how it connects, how it can connect, if we define it appropriately, to this very natural and meaningful idea of area. Extremely natural geometrically. So, let me say that a little bit differently. We took a geometric concept that we care about, that we need to be able to get our hands on. We defined our algebraic construction based on the pre-existing geometric concept. Yep? Okay. All right, so we're going to do the same thing here. When deciding what that should be, let's think about what geometric thing it might relate to. And I like to view displacements. I mean, there's different points of view on how you can do this, and you can do this with velocities, but I think it's easier to see with displacements. What is it about? How do displacements relate to each other? What might I really naturally need to be able to do with displacements? Let's define addition to be based on that, right? And so here's what I think is a very natural candidate. This first vector, if that represents a displacement, right? This second vector, if that represents a displacement, let's entertain the possibility of what would happen if I were to start at that point, and if I were to combine, if I were to compose, if I were to first displace as instructed by V, and then, having done that, from that point, then subsequently displace myself as indicated by W. And the result would be, well, first, I'd end up there. And then second, from this point, the result of my V displacement, if I then do what W says, right, then altogether, grand total, you might say, right, I get to there. So altogether then, let's see here, I'll use blue. I'm going to define the sum of these two vectors to be the result, to be the vector that represents the result of the composition of these two displacements. Combining the displacements. Doesn't that seem extremely natural, right? I mean, this idea, what do you do if you're dealing with displacements? Well, you might displace yourself and then you might do another displacement. It's ultra natural physically. So we now have a definition of addition that is motivated by, our physical use of vectors. Okay. By the way, I don't know about y'all. When I was in high school, they showed me this whole head to tail thing, but they never connected it to displacements, and so I just thought, well, what a weird choice. So you're going to stick the head of this one on the tail of that one. Strange, but that's the formula, I guess. Or it just seemed like an arbitrary convention. But I think it's important to realize it's not arbitrary. This is extremely natural in that context of that interpretation. Okay. All right, so that's our definition for vector addition. Okay, now with that settled, we've decided what vector addition means. Next question, how do you compute the sum of two vectors? And this I'm going to say is a little analytic geometry problem. Just write down the coordinates, make some little triangles, some similar triangles, play the game, and this is the formula. It's not hard to check. That's another good exercise. Right? Draw the vectors that are represented by, V1 and V2 and W1 and W2. Make little triangles, move triangles around. It's not hard. Give that a try. Make sure you can do this. Okay. All right. So I'm going to call this good news. The reason I'm going to call this good news is this formula. I mean, look how aesthetically convenient it is. If you want to add two vectors, you just add the first coordinates, and then you add the second coordinates. How easily implemented that is. Isn't that nice? Here's another common mistake. A lot of people mistakenly, in my opinion, very mistakenly think that the fact that this is easy to implement is why we add vectors this way. And I'll point out that smacks of, 6-year-old me, had this idea of, well, wouldn't it be easy to implement multiplication if we just made 4 times 7 equal to 47, right? How easy it is to implement, not the point, right? So this is not why we add vectors the way we do. This is a fringe benefit. That's not why. This is why. Everybody on board? All right, how do you multiply two vectors? Again, let's connect it to intuition. If you have a displacement, which is to move in a certain direction by a certain distance, what should C times that be? It's a choice, right? You get to define, whatever seems reasonable, but I'll tell you what I think is reasonable is that C times moving in a certain direction by a certain magnitude would be moving in that same direction by C times that magnitude. That just seems reasonable to me, right? So that's a choice, right? It's a classical. It's a standard choice. This is the choice that everybody else makes. So we have to get on board with it, right? But I just would like to point out that this is a reasonable choice. And then having made that choice, having drawn this picture, you can then make a similar triangles argument and persuade yourself pretty comfortably that this is the convenient algebraic formula. And again, now, this, you could have said, hey, what would be the, from the elementary school me point of view, what would be the easiest way to make sense out of this? It seems like it'd be pretty easy how about I just multiply C times each of those? That'd be an easy little formula to write down, right? And so we got lucky. Yeah, it turned out to be nice and easy. But let's not motivate this because the formula is easy to implement. That's a lucky break, right? The reason this is the formula is because it corresponds to a natural geometric picture. All right. Okay, here is a great little exercise. Try to prove this theorem that the magnitude of a scalar multiple of a vector is the absolute value of that scalar times the magnitude of the original vector. Now, here's the thing. In order to prove this, you need formulas for how to evaluate stuff. Well, we just wrote down a formula for how to evaluate CV. Right? And we have elsewhere a formula for how to evaluate a magnitude. So all the objects in this proposed in this candidate statement here, this theorem that we want to prove, all of these formulas are well defined. So this is just a matter of cranking out the algebra. A lot of people make the classic blunder of thinking, okay, well that C will just factor out, and then they lose the absolute values. But very importantly, that does not work. For one thing, just as a sanity check, this being a magnitude has to be positive. There's no such thing as a negative magnitude. Right? That is a magnitude. It has to be positive. So whatever it is that's here, it's better be positive, right? If that's negative, it's clearly garbage. Now, that's not why we put the absolute value in there. We don't put it in there to avoid a sanity check violation, right? There is an algebraic reason why it's in there. I'm just pointing out that if you don't put it in there, you're clearly wrong. Right? Okay, so now why does that actually come up? Another sort of underappreciated fact, high schools, I don't know, I shouldn't speak too broadly, but, when I speculate about high schools based on my own experience, long ago. And what I see students doing in my classes currently is that high schools are really, really sloppy when it comes to the algebra of absolute values, the algebra of inequalities, this kind of stuff, right? They let you get away with a lot of murder in this area, and this is not good. Okay, so gotta be really careful with this algebra. So anyway, here is a good point to be aware of. A lot of people present square roots as undoing a square, and that is a statement which is sometimes true, but not always true, otherwise known as not true. Right? So don't make the mistake of misinterpreting. The square root of k squared is not necessarily k. Certainly, claiming that it's k is a wrong formula. The right formula is that this is the absolute value of k. And let me make sure we're clear on one little bit of notation. This symbol right here, a lot of people mistakenly interpret this. That does not mean both square roots of the given number. This specifically means the positive square root. That's what that notation means. And if you want, for whatever reason, to refer to both of them, that's why you'll see very often written this thing right here. That means both of them. This one up here strictly means the positive one. Everybody okay on that? Okay, so anyway, I just want to make sure we're clear on that. Again, at my high school, it was just the Wild West with square roots and absolute values and all this kind of stuff, and you got to be real careful with that. So, okay, with this in mind, take this, go through the algebra, confirm that you get this. Good enough just to do it for vectors in R3. Right? You don't have to do it for Rn. It's just notationally awkward. But write down, for a general vector v in R3, prove that this theorem is true. And specifically note where the absolute values come from. Okay, so it's a good exercise. Again, I hope you all will actually do that. How do you subtract? There's a couple different ways to interpret subtraction. You can first note that subtraction is a combination of things we've already defined, right? It's a scalar multiplication by -1 followed by an addition. We've already defined scalar multiplication. We've already defined addition, so everything else follows. So we don't get to define subtraction. We don't get to speculate on what do we feel like ought to be, the definition. And, think about physical applications. It is what it is at this point. But here's a convenient way to think about it, and I'm a big fan of this. If you take these two vectors, w and v minus w, what do you suppose happens when you add w and v minus w? Whew, you better get v, right? Or else our algebra that we're creating here would be a nightmare. Right? So conveniently, you do, but the point is that this gives us a nice way to think about subtraction. The difference, v minus w, given a vector v, given a vector w, is that vector there. It's what you might call, you put both vectors in standard position and go from one head to the other head, specifically in that order. Okay. All right. Again, the way I remember it is v minus w is the thing that it has to be such that when you add to w, you get v. That's by far the easiest way for me to think about it. Okay. There's a different way you can think about it. Anyway, y'all can read this and make sense out of it if you like. We just don't have time to talk about it, but it's not critical. Okay. A little bit of algebra. Here's a flashback to some of the most boring stuff you ever saw in middle school, maybe even elementary school. Do y'all remember when they wrote down a bunch of formulas like this? A plus B equals B plus A, and we had to learn that had a very big, important sounding name. That's the commutative property of addition. And I just remember thinking, wow, what a big name to associate to such a small concept. Right? What could be more obvious than that A plus B is equal to B plus A? Do y'all remember thinking that? I assume you did. Okay. Anyway. So there's a temptation to look at these formulas and think, well, duh, I've known that since I was 11. Right? But no, you haven't. These are all brand new formulas. Let me remind you, this addition here is brand new as of today, right? So now y'all have previously done an addition of real numbers that, yes, you have been doing since elementary school, absolutely, right? But this, now we use the same little symbol, which is really get right down to it, a little bit inappropriate. We're using the same symbol to represent a different, newly defined thing that we just got through doing. But, despite the fact that we use that same symbol, it is a brand new operation. So the fact that this operation has this commutative property, not obvious, right? That's a little algebra problem to confirm that that's true. Now, good news, yes, it is true. Right? But this does require a proof, and the way you prove this is no big deal. You just write down, look, we have a formula for that. That is V1 plus W1, V2 plus W2, V3 plus W3. Right? And this, we have a formula. For W plus V, it's W1 plus V1, W2 plus V2, W3 plus V3. Right? And so the question of whether these two vectors are equal boils down to the question of, are these ordered triples equal to each other? Okay. Well, two ordered triples are equal to each other if and only if each of the individual numbers. So now what I've got it down to is I just have to confirm that that's equal to that, and that that is equal to that, and that that is equal to that. Now, how do I know that those three things are equal as paired there? And you might be thinking, okay, we've turned one question about commutativity into now three questions about commutativity. How does this help us? And, of course, the way it helps us is that these questions here are commutativity of real numbers, which we've already long since accepted back in elementary school. And so these are, in fact, obvious. Right? So those coordinates are equal. Therefore, these triples are equal. And therefore, these vectors are equal. And our formula is verified. Everybody see how that works? So this kind of an argument, by the way, is just very commonly referred to as, we'll just break it down in coordinates. You can see that's all that happened. I took a vector operation and I rewrote it as operations in coordinates, and I just look at the coordinates. Right? So a coordinate-wise approach, sometimes we say. Very often, really convenient way to get stuff done. Okay, I would suggest it'd be a good exercise for y'all to copy, mimic anyway, work by analogy, the argument that I just showed you there, and prove, at least one of these. Same sort of thing. But just make sure that you can, see how to actually write that down. And let me give you all a warning. Y'all have probably heard this kind of thing before, but it's dangerous to look at something like one of these and think, oh yeah, I can see how that would work out. Right? Because two things. First of all, okay, maybe you can kind of see how that would work out, but how are you really, really sure that what you think you're seeing, that the sort of pattern that you're noticing, are you sure that that's actually going to work in these cases? Or maybe something's a little bit different in one of these. Right? Don't get too overconfident about that kind of thing. The other thing is, the exams in this class are going to be written exams in class. In class is a finite time period, therefore they are timed exams, and so therefore the point is you need to be able to reproduce, you need to be able to talk about math, get stuff done, solve problems in a timed context. And the process of writing down clearly, effortlessly, smoothly, a mathematical argument requires practice. And thinking about it in your head and thinking, oh yeah, no, I could totally do that, right? That doesn't give you that practice, right? And so you're depriving yourself of an opportunity to get that practice. So, write it down, think it through, make sure it actually works, and then look at what you've written down and ask yourself, is that the most elegant way to have written that down, or is this kind of awkward in a way? Can I improve my writing here? Could I have said that in a way that is more sort of crisp and to the point, or did I meander unnecessarily about something that, now that I think about it, is not at all important, or is that kind of thing? So give me 2 seconds. So it's a good opportunity to practice. You need the practice. Give yourself that practice. Yes.
So I guess instead of breaking these down into their coordinate kind of systems, would it be possible to just do it graphically and kind of do that representation?
So sadly, graphic, I'm going to air quote proofs, right, have the unfortunate feature that they are very closely related to proof by example, right? And proof by example is logically invalid, right? Because you can only draw one picture. That's the problem, right? When you're doing algebra, you can say, this variable here that I'm calling V1 could be any real number, right? But when you draw the picture, you're specifying a single case. So proof by example, just not a valid proof argument. What you're thinking of is something I do strongly encourage. I think it's a great idea to draw the picture and try to have a geometric intuition for why it does feel like it ought to be true, right? And I'm all for that, but it's rarely a good way to actually make a proof. Yeah, it's a great question. Thank you for that. Anybody else? Okay, a couple of little mishmash of different things I've got to throw in here real quick. We're going to be doing a lot of stuff in this class with things called unit vectors. Unit vector is just a vector of length 1. I'll say magnitude 1. By the way, when we say length, very often we mean magnitude. It's just sort of an alternative terminology. Anyway, it's fine. So any vector whose magnitude is 1 we call a unit vector. And it turns out this matters for reasons that will become clear much later. Right? Anyway, this is a concept sufficiently important to have a name. The name is unit vector. Here's some examples. 1, 0, 0 is a unit vector. This weird-looking little fellow, multiply it out. Believe it or not, how it turns out with the arithmetic, that is a unit vector. And go ahead and crank out that arithmetic. Everyone should do that once in their lives. It's nice how that works. A little bit of notation. The book uses I, J, and K to refer to the three vectors along the coordinate axes. So the book uses I with a little hat, J with a little hat, K with a little hat to represent the you might call the coordinate unit vectors. Also called the standard basis vectors. Very common terminology, standard basis vectors. The little hat is supposed to be a sort of a recognition for the reader that they're not just vectors, they're unit vectors. Okay, that's fine. I have a different preferred notation for this. By the way, very standard. I did not make this up. But this, instead of calling this I, call it E1. Instead of J, E2. Instead of K, E3. And you might think to yourself that, that seems clunkier, right? I mean, IJK, boom, right? It's just very natural, familiar, alphabetically convenient, and writing subscript seems unnecessarily heavy-handed, right? Until you start doing math in RN, at which point E1, E2, E3, E4, E5, E6, E7, no, not that big a deal, right? What are you going to do with the alphabetic strategy? I, J, K, L, M, N, O? What if you're doing R74? You run out of letters, right? It becomes a little preposterous in the long run. So anyway, I like the E notations. The book's going to use I, J, K. They're both fine. Okay. Neat fact. I'm going to leave this proof as an exercise for y'all to follow through. But if you have a non-zero vector, then this little construction right here, right, your non-zero vector, take that vector, divide it by its own magnitude. This construction here is a unit vector. And not only that, it's the unique unit vector that points in the same direction as that original vector. this is a very handy, it's going to be used so much, it's a very important little construction, taking a vector and dividing it by its own magnitude. Here's the proof. Well, anyway, y'all can read this proof that it gives you a unit vector. Notice the way we prove that this is a unit vector is we confirm that that vector's magnitude is equal to 1. That means unit vector. So it becomes an algebra problem. It's just a matter of working it out. Okay. Last, real quick comment. This construction here comes up just an enormous amount. It's going to come up very significantly in Math 212. It's going to be the main subject of discussion in Math 216. It's the cornerstone concept of linear algebra, which is one of the big things we do in Math 216. This idea of a linear combination. And so here's what it is. If you have a collection of vectors, V1 through Vn, taking a sum of scalar multiples of those vectors is called a linear combination. And so very often we'll talk about, what happens if you know this vector is a linear combination of the other two vectors. Linear combination is just a convenient way to say this is a sum of scalar multiples of these other vectors. So it turns out extremely important. It's going to come up a lot, so I had to define this terminology. And here's an easy example. This is an easy one to verify, by the way. The vector ABC is a linear combination of E1, E2, and E3. Weirdly, these coordinates of the vector happen to also be the coefficients in that linear combination. And this is one of the reasons that these vectors here, E1, E2, and E3, are considered important. It's because they are the unique vectors that have this feature, such that when you write something else as a linear combination of them, the coordinates are the coefficients. Nice feature. Anyway, check and make sure that this formula is true. Make sure that you can persuade yourself that this blue circled formula is true. And that'd be the last thing for today. We will pick up here on Monday. Y'all have a great weekend. Yeah.
Can you explain where the E is coming from? It's the same E.
Yeah, hang on a second. Let me just stop the recording here real quick.